Welcome! In this video, I'll show you how to solve Griffiths problem 7.11 as it appears in the third edition of the book's Introduction to Quantum Mechanics. Now, this problem asks us to do the following. It says, find the lowest bound on the ground state of hydrogen you can get using a Gaussian trial wave function. And of course, that sort of wave function is precisely what we have here. So, for example, a normalization constant A times e to the minus b, which is an adjustable parameter, times r squared. So what we need to do is, of course, well, normalize this wave function. And then we need to use the variational principle, which, as you recall, means finding the expectation value of the Hamiltonian for this configuration, right, for this particular wave function. And we know that that will always give us an overestimate for the ground state. So for that reason, then we need to take the derivative of this energy, set it equal to 0, and thus we will find the value for B that minimizes it. So that is what we have to do. So let's begin by normalizing this wave function. So 1 is going to be equal to the integral over all of space, and we are in hydrogen, so it's going to be a spherical integration, right, over spherical coordinates. So we have to go from 0 to pi in phi, 0 to 2 pi in theta. Sorry, the other way around. So 0 to pi, I guess it depends what you call them. I call them like this, so this would be theta for me. 0 to 2 pi is phi for me, and 0 to infinity is r. So this would be a squared e to the minus 2br squared. And of course, r squared and sine theta, don't forget about it, we are dealing with spherical coordinates. Okay, so the phi integral is trivial, it's just 2 pi. The theta integral is simply the integral, so I theta. This is simply integral from 0 to pi of sine, which of course is minus cosine, and evaluated between 0 and pi, we get minus. At pi it is minus 1, and at 0 it is 1. So we get 2. So of course, from the angular part, we get the 4 pi that we are used to. And we can pull the a squared outside. And now we're left with the radial integral, e to the minus 2b r squared dr. Now there's two different ways to, there's of course more. I'm going to show you two different ways to integrate this. So method 1 is going to be this. So I don't know, 1. So it's going to be integration by parts. So the easiest way to do this, and in fact, it is the best way to do it, I think, is to just say u is going to be r, and thus du will be dr, and the v is going to be r e to the minus 2b r squared. And the good thing about this is that now finding the v is quite easy because, well, it's simply, if you have e to the minus 2b r squared and you take its derivative with respect to r, then you would get minus 4b r times the same exponent. So basically, we only need this minus 4b. So we have to divide by it. So we get e to the minus 2b r squared over minus 4b. So there we have the v and v, and this was quite an easy way of doing it. Trying to use u equal r squared and dv e to the minus 2b r squared dr, it doesn't lead you down a good path. You can try it, but you're going to see it isn't really that good. So now let's do integration by parts. So product of these two, so the actual integral will be the product of these two. So we get minus r over 4b times the exponent. But all of this is going to be 0 because we're integrating between 0 and infinity. At infinity, the exponential goes to 0, and at 0, this goes to 0. So this entire thing is 0. Then we have minus this product. But there's already a minus sign here, so it goes to plus, and we're left with 1 over 4b, integral from 0 to infinity of e to the minus 2b r squared dr. And this is basically a Gaussian integral, but, and this is a big but, don't make this mistake, the Gaussian integral goes from minus infinity to infinity, not from 0. So we have to use a little trick and say that, well, since this is an even function, then what we have here is simply half of the entire thing. So it is half of the integral that goes from minus infinity to infinity. And now we have a Gaussian integral. So now we have 1 over, 8b, of course, times and the square root of pi over 2b. Okay, I've said before, it's incredibly important that you remember that this sort of integral is square root of pi over beta, well, whatever is here, right? Whatever is here ends up being in the denominator. You have to learn that. It's going to come up super frequently, so you need to learn that. I cannot emphasize it enough. Okay, so this is the result from the integral with the first method. Let's now go for a different method. So a different way to solve that integral, so let me copy it. So the integral is there. 0 to infinity of r squared e to the minus 2b r squared dr. So that is the integral that we are solving. So a different way of doing it is basically what we have done in the past, right? Which is saying, all right, let's call this integral from 0 to infinity of e to the minus beta r squared dr. And then we notice that if, and r squared. And then we notice that if we had e to the minus beta r squared, and we take the derivative with respect to beta, then what do we get? Then we would get minus r squared e to the minus beta r squared, which is basically the same thing that is here, except for the minus sign. So we can replace what we have here with minus by the beta, which we can pull out of the integral, right? Because it doesn't depend on r. And then we have e to the minus beta r squared dr. And the good thing about this is that now this is a Gaussian integral. And again, kind of, because we are once again going from 0 to infinity. So we need to say that that is 1/2 of the integral that goes from minus infinity to infinity. And that is the integral that we know the value of. So now let's just put it in here. So minus 1/2 the beta of square root of pi over beta. Okay, and let me rewrite this. So I'm gonna put the square root of pi outside because, you know, it doesn't depend on beta. And I like to write out my beta like this. So minus 1/2. It makes it easier to take the derivative. But again, it doesn't matter. So we take the derivative of beta, so we get a minus 1/2, so we get 1/4, the negative goes away, there's still a square root of pi, and then we have beta to the minus 3/2, but beta is 2b, so we get 2b to the minus 3/4. Now, what is this? Let us rewrite it. So times square root of pi. And what else? So then we have 1/2b times square root of 2b, right? That simply separated this 3/2. So now we can multiply a little bit and we get square root of, actually I'm gonna purposely write it like this, 1/8b times the square root of pi over 2b. And this is precisely what we had found before, right? 1/8b, square root of pi over 2b. Exactly the same. So these are two methods. You can use whichever one makes you happy. But either way, the result of this integral, this thing right here, is 1/8b times square root of pi over 2b. So now finding a squared is easy peasy. So let's just leave it alone so we can simplify a little bit. This 4 and this cancel out. So we are left with 2b over there. Then we have pi to the 3/2 and b to the 3/2. Wait, oh yeah, but b to the 3/2 is up here, sorry. Right, am I going insane? No. And 2 is also to the 3/2. Okay, so we have 2b over pi, all of this to the 3/2. And this is what a squared is. Of course, you could take a as well, which would be the square root of that. But we will always encounter a squared and not a. So, I mean, there's really no point in finding a over a squared. Okay, so let's get rid of all of that. And now that we normalized our wave function, we can actually begin solving the problem. So what is the Hamiltonian here? So the Hamiltonian is, of course, the Hamiltonian of the hydrogen atom, which we know is minus h bar squared over 2m del squared minus e squared over 4 pi epsilon 0 times 1 over r. So if we want to take the expectation value of this, we need to take the expectation value of each part. Actually, I'm going to leave the minus sign. Whoops. I'm going to put the minus sign inside. So it's going to be basically plus minus e squared. It doesn't matter. It's just the way that, that way I don't get confused. So this is what we will call, of course, t, the kinetic part, and the potential part. We will solve them separately because they take a while. And, you know, it's going to be too much to have everything at once. So let's begin calculating the kinetic term. So this would be the integral over all of space of our wave function, which is a e to the minus b r squared times minus h bar squared over 2m del squared of our wave function, a e to the minus b r squared, and times dr3, right, over all of space. And now we need to define what our coordinates will be. What coordinates should we choose? And of course, we will choose spherical coordinates because choosing anything else would be just mad. Don't do it. So del squared in spherical coordinates is 1 over r squared d by dr of r squared d by dr of our wave function, right? So this acting on our wave function means we'll have here a e to the minus br squared. So we need to calculate this. So let's do it. So 1 over r squared, this hasn't changed, d by dr, r squared times. Well, actually we can pull out the a in front. So the derivative of this here will have minus 2br e to the minus br squared. All right, now multiply through by r squared, and we get r cubed. Now we need to take that derivative. But before we do that, we can factor out minus 2b. That way, everything will look a little bit cleaner. You don't need to do it, but it's a little bit cleaner over r squared. And now we take the derivative. Actually, let me rewrite it first. So r cubed e to the minus br squared. Okay, so now let's take the derivative. And if we do that, we get 3r squared e to the minus br squared. And then we get plus the derivative of the exponential, right, times r cubed. And the derivative of the exponential is minus 2b r e to the minus br squared. Okay. So here we get minus 2ba over r squared, 3r squared. We can factor out the exponential, minus 2br to the fourth e to the minus br squared. So this is our result. We could multiply in this r squared, but we are going to have another r squared from the d3, right? From r squared sine theta. So those two r squares are just going to cancel out. So it doesn't really matter. You can multiply through, but it's going to be the same. I just like to let this one cancel out right away. Okay, so let's put this into our equation for the expectation value of t, which will now be integral from 0 to pi, integral from 0 to 2 pi, integral from 0 to infinity of, and now let's pull all of our constants outside, at least minus h bar squared to m and a. Then we have e to the minus br squared, and now comes what we just found. So minus 2ba over r squared times 3r squared minus 2br to the fourth times e to the minus br squared times r squared sine theta dr d phi d theta. Okay, so there's a lot we can simplify here. So first of all, this r squared cancels out with this. We can easily calculate, as before, the integral of sine theta d theta and d phi, which gives us a 4 pi. So 4 pi. And then we can take this outside and put it together with this. When we do it, the minus signs cancel out and the 2's cancel out, and we get a squared. So basically we get a squared h bar squared b over m. Okay, and then we have the rest of the integral. So integral from 0 to infinity, we can put both of the exponentials together and we get two terms. We get 3r squared minus 2br to the fourth times e to the minus br squared dr. Okay, so we have two integrals, which I will write down explicitly, I think. So we have 3r squared e to the minus br squared dr minus 2b. Actually, if I'm already writing like this, I'm going to put the 3 out here. So minus 2b integral from 0 to infinity of r to the fourth e to the minus, oops, it's 2b, by the way, 2b, r squared dr. Okay, so these are the integrals that we now need to solve. Now notice this one right here. Oh, I erased it, but it's the same that we had before, actually. And this one right here is a little bit longer. It's r to the fourth. So let's use this one. Again, there's two methods. This time I won't show you both because it's the same as before. You can either use integration by parts or you can use substitution. I will use substitution. So for that reason, you have to notice that this is basically the exact same thing as before. So if we take e to the minus 2br squared and we call 2b beta, and we take the derivative of this with respect to beta, but this time twice, what do we get? We get, from doing it once, we get minus r squared, and from doing it twice, we get it again. So if we take the derivative with respect to beta twice, we get r to the fourth power e to the minus beta r squared, which is exactly the same that is here in what I will call I2. So I2 is equivalent to an integral from 0 to infinity of e to the minus beta r squared dr, but taking the derivative with respect to beta twice. And we know what this integral is, right? We use the trick. We say it's 1/2 of the Gaussian integral, which goes from minus infinity to infinity, e to the minus beta r squared dr. And what is this? Well, this is going to be 1/2 times, let's see. So it's going to be two derivatives with respect to beta and then square root of pi over beta. Now we take one derivative and we get minus 1/2 times 1/2 times square root of pi, right? This came from taking the derivative. And then we still have another one. So we get the beta of beta to the minus 3/2. So when we take another derivative, we get 3/2 times, so minus 3/2, sorry. So the minus cancel out, and we get 3/2 times 1/4 times square root of pi times beta to the minus 5/2. So this is going to be 3/8 times square root of pi times 1/2b to the 5/2 power. So this is the result for I2. And as you can see, these sort of integrals are extremely quick if you do them like this. So let's plug it in here. So instead of this, we get 3/8 square root of pi times 1/2b to the 5/2. What about I1? Well, I1 we already solved before, but we're gonna just do it quickly because I erased the result. So I1 is integral from 0 to infinity of r squared e to the minus 2b r squared dr. Once again, we will use the beta trick, right? So we will say, okay, this is minus the derivative with respect to beta. Before we didn't have this minus because we did the derivative twice, so the minus canceled out. And this is of 1/2 of the integral from minus infinity to infinity. I'm going a bit quicker. E to the minus, this would be beta, r squared dr. So this would be minus the beta, well, 1/2, of course, square root of pi over beta. Now we take the derivative, we get another minus 1/2, so we get 1/4 square root of pi times beta to the minus 3/2. But now we plug in the value of beta and we get square root of pi over 4 times 1/2b to the 3/2 power. Okay, so let's plug it in. So this is pi over 4, so square root of pi over 4 times 1/2b to the 3/2 power. Okay, so let's now go to the right and notice we can factor out quite a few things. So we already have this 4 pi over m and a squared h bar squared b, but we can also factor out a square root of pi, and we can also factor out, let's see, if we cancel this 2 with this, we are left with a 4, which we can then factor out. So we can factor out a 1/4. So now this is gone, this is gone, this is gone, and this is gone. Now, what else? We can factor out the b's, because we have b here, and this is b to the 5/2. But after we cancel it out, we get b to the 3/2, which is the same that we have here. So we can factor out 1/b to the 3/2. So this is gone, and this is gone. And then what do we have left? We have 2 to the 5/2, which is basically 2 squared, which is 2 to the 4/2 times square root of 2. And here we have 2 times square root of 2. So we can factor out square root of 2. What does that leave us with? Oh, and we can also factor out a 3. So we can factor out a 3. So that leaves us with 1/2, right, from here, and minus, let's see, 1/4 from this. And we covered everything. So now let's begin simplifying. So we can simplify these two 4s, so this with this. We have b here and b here. So this will be b to the 1/2 instead of 3/2. Then we have pi and square root of pi, which will be square root of pi to the 3/2. But we haven't even plugged in the value of a yet, actually. And what is this? This is going to be 1/2, or basically 2/4 minus 1 over 4. So this is positive 1 over 4. So we get 3 over 4, right? This one, times pi to the 3 halves, h bar squared m b to the 1/2 square root of 2. And now we plug in the value of a squared, of course, which is this thing right here, which is 2b over pi to the 3 halves. So it is 2b over pi to the 3 halves. All right. So what does this mean? This means that we have square root of 2 and 2 times square root of 2. So basically, this cancels out this, but we are left with a 2, right? It only canceled it out partially. We still have this 3, so times 3. We have the divided by 4, but we can simplify this, so we get divided by 2. So we already considered that. Then we have pi to the 3 halves, pi to the 3 halves, b to the 1/2, b to the 3 halves, so we get b. Then we have h bar squared, and then we have divided by m. So there we go. This is the expectation value of the kinetic term. But we still have to do the potential part, right? Now, don't worry, the potential is much, much, much easier. The kinetic was the difficult part. So let me go off to the side and let's calculate the expectation value of the potential. So the expectation value of the potential is minus, actually, once again, let's go into the integral. So we get a e to the minus br squared times minus e squared 4 pi epsilon 0 r, and then a e to the minus br squared dr3. Now let's choose spherical coordinates. So we go from 0 to pi, 0 to 2 pi, 0 to infinity. And actually we can pull out all of our constants. So we get minus a squared, e squared, 4 pi epsilon 0. And we are left with e to the minus 2 br squared times, and what we have here, we have r squared, so 1 over r, and r squared sine theta dr d phi d theta. But the r's cancel out partially, and we know what the integral for d phi and d theta is. It's going to be 4 pi, which cancel out the 4 pi that is under here. So we get minus a squared e squared divided by epsilon naught. And we only have the integral from 0 to infinity of e to the minus 2b r squared r dr. And now this is a much simpler integral that we had before. To solve this integral, the easiest way would be to use substitution. So we could say u is going to be minus 2b r squared, and du is going to be simply the derivative of this, which is going to be 4b r dr. So we can put this into this equation. And we get, well, let's see, the bounds. When r is 0, u is 0. But when r goes to infinity, u goes to minus infinity. And then the exponential will be e to the u. And r dr is now minus du over 4b. So du over 4b with a minus sign, which will cancel out this minus sign. Now this integral is easy. It's e to the u, right? So it's e to the u, nothing new. So we get a squared e squared divided by 4b epsilon 0 times e to the u evaluated between 0 and minus infinity. So at minus infinity, it is 0, but at 0, it is 1. So we get minus e squared 4b epsilon 0, and let's put in the value for a squared, which is 2b over pi to the 3 halves. And let's see. So then we have minus e squared. How can we simplify this? We can take the 2 outside. So we get 2 times square root of 2 times b times square root of b. And what else do we have? That's kind of it, right? We have epsilon 0, but the square root of pi is going to be there. So square root of pi cubed, basically. Yeah. Oh, wait, what happened to the 4? So there's a 4b that I almost forgot about. Okay. So here we can simplify this a little bit, but not that much. So we can get minus e squared, the b's cancel out, and we can leave this as 4 pi epsilon 0, right? Taking 1 pi out of this, so pi times square root of pi is basically what I did. And then we have times 2 times the square root of 2b over pi. So we considered this. Yeah, I used the notation, which is the same that appears in Griffiths. And just so that you see, of course, you can simplify this 2 with this, and you get 2 pi epsilon 0, right? But this way, it's a little bit tidier. 2 pi epsilon 0. So there we go. This is the expectation value of the potential, which, as I mentioned, was much, much faster than the previous one. So now let's put everything together. So the expectation value of the Hamiltonian, it is what we got in the kinetic part, which is this 3b h bar squared over 2m. So 3b h bar squared over 2m, and then we get our result here, which was minus e squared. So minus e squared divided by 2 pi epsilon 0 square root of 2b over pi, I think, right? Yes. So this is the energy, but now we want to minimize this. We want to find the value for b for which this is the smallest amount possible, because we want to get as close as we can to the ground state. So we take the derivative with respect to 0. Oh, sorry, with respect to b, but we set it equal to 0. And that's 3b. Okay, so sorry, the b falls away, so h squared 2m. Actually, it was correct like that. Then minus e squared 2 pi epsilon 0 square root of 2 over pi, and then the derivative with respect to b of b to the minus 1/2. That's going to be, actually it was 1/2 back then, now it is minus 1/2. Okay, and this has to be equal to 0. So now let's put it on opposite sides. So we get 3h bar squared over 2m. This is equal to e squared divided by 4 pi epsilon 0 square root of 2 over pi, 1 over square root of b, basically. Okay, so we can simplify a few things, this with this, and that's actually, I think that's it. Well, now let's solve for b. So square root of b is e squared times m times the square root of 2 divided by 3 h bar squared times 2 epsilon 0 times pi and times the square root of pi, I guess. Let's see, so m is here, 3 is here, h bar squared is here, e squared square root of 2, that's 2 pi epsilon 0 square root of pi. Okay, we considered everything. So now we can see that b is going to be the square of this. So 2m squared e to the 4th divided by 3 squared, which is 9, h bar to the 4th times 4 epsilon 0 squared pi squared times pi, so pi cubed. And we can simplify this 4 with this 2, so we get 2 here. I guess we could write it as 18, but it's okay. Now we want to plug this into our formula here. So what do we get? I'm going to zoom out just a little bit so I can copy it easier. So the expectation value of the Hamiltonian is 3 h bar squared over 2m. times b, which is right that thing there. So m squared e to the fourth 9 h bar to the fourth times 2 times epsilon 0 pi cubed. And then we have minus e squared over 2 pi epsilon 0 square root of 2b over pi. But of course, what is the square root of b? We also know that. So square root of b is this thing. So m e squared square root of 2 3 h bar squared 2 epsilon 0 pi square root of pi. Okay. Now we can probably simplify a few things, but there isn't really all that gigantically much that we can do here. Let's see. So 3 h bar squared m squared. Yeah, we can't really simplify too much here. So the m's a little bit. So we get 3m, right? This with this. H bar squared e to the fourth. And then divided by 4 times 9 h bar to the fourth epsilon 0 squared pi cubed. And then we get minus e to the fourth m. We have square root of 2 squared, so we get 2 divided by 2 pi squared from this and this epsilon 0 squared. So we consider this and this. Now there's another 2 and a 3, so 2 times 3. There's pi square root of pi squared, so we get a pi cubed. And we get a pi cubed. And then we have h bar squared. And I think we considered everything, right? Yeah, oh, I didn't notice I could simplify this, by the way. So h bar squared, of course, and h bar to the fourth, we get h bar squared. So now we can factor out a few things. So we can factor out m e to the fourth, and we can factor out a 4, right? So from this and this and this. And even a 3, if we write this 9 as 3 times 3. So 4 times 3, epsilon 0 squared, pi cubed, h bar squared. So after factoring out all of that, we get 3 minus 3 divided by 3 minus 2, right? This divided by 3, we already factored out. Yeah, so 1 minus 2, basically. So we get minus, actually I'm running out of space, so let me do it down here. So minus m e to the fourth over 12 epsilon 0 squared pi cubed h bar squared. And this is in principle correct, but we would like to have an actual number. And unless you want to plug every single number into the calculator, we will have to do a little bit of algebra here. So let's recall that the energy for the ground state of hydrogen has the following formula. So it's minus 2m over 2h bar squared times e squared over 4 pi epsilon 0 squared, and times 1 over n squared, of course, but we are at n equals 1. So here we can see that we have a lot of similarities. So rewriting this kind of the way we have it, we have m e to the fourth power, right? Here, check. Then we have h bar squared right here, check. But then there's a few differences. So here there is a 32 that we don't have. And here there is pi squared epsilon 0 squared. So there's a few things that we need to write differently. Whoops, I got rid of the squared. So let's write this in the same way. So minus m divided by 2h bar squared. So now this 12 we wrote as 6 times 2 basically, and the 2 is right there. So now we want to go for this next part, the parentheses. So here we have e squared, easy, because this thing is gonna be squared as well. Down here we have pi and epsilon 0, but we still have 1 over pi remaining. So this is now considered, so is this, and so is this. But now we need a 4, and we only have a 6 left. So something you could do, for example, is you could write this. We don't only need a 4, we need a 16 actually. So what do we have? We have a 6 left. We can write it as 3 times 2 and multiply by by 8 divided by 8. Because if we do that, we will have 8 divided by 3 times 16. We put the 8 divided by 3 here and the 16 in here, right? In the form of 4 squared. So when we do this, we will have E1 from all of this times 8 over 3 pi, which we can easily calculate because E1 is minus 13.6 electron volts times 8 divided by 3 pi, which gives us approximately minus 11.5 electron volts, which is our estimate here. And of course, we have overestimated the ground state, but you know that's what this does. But as you can see, it was relatively easy to do. We didn't have to solve, at least when you compare it to solving the hydrogen atom, right, which is a traumatic experience. So all we did was we normalized the wave function. We wrote this thing right here, right? We need to find the expectation value of the Hamiltonian with respect to our trial functions. And we did that, right? We found the expectation value of the kinetic part, which was a bit longer. And then we went for the expectation value of the potential, which was actually quite fast. Then we plugged it in, took the derivative with respect to b, set it equal to 0, found b, plug it back in to find the minimized value of the energy, which is this, right? We then had to simplify it a little bit. And that's it. So I hope this was useful. If it was, make sure to leave a like on the video, comment and subscribe. Maybe share it with your classmates. It would really help me out a lot so I can continue to make videos like these. So I'll see you in the next video. Thank you very much for watching.